Okay, so first let me thank the organizers of this nice workshop for inviting me. It is a pity that we cannot be there in Mainz. It's such a beautiful city, but okay, hopefully we will be able to meet in person very soon. All right, so today I'd like to tell you about the microwave spectroscopy of hybrid superconductor semiconductor qubits with Majorana 0 modes. I'm going to focus on the NANOWIRE platform. I don't need to spend much time on this platform. I'm sure that most of you already know about these semiconducting nanowires with strong spin orbit coupling, and how if you apply a magnetic field which is perpendicular to the spin orbit axis, you create helical bands. And when you proximitize these helical bands with a standard S-wave superconductor, you end up with an effective P-wave superconductor. This is essentially a realization of a famous Kitaev model for one-dimensional P-wave superconductivity. And as you all know, this model contains a topological phase. For this particular realization, this topological phase occurs when the Zeeman field is larger, is above the critical field here, written here in terms of the superconducting gap and the chemical potential of the semiconducting wire. And the idea is that in this topological phase, we expect that this nanowire will have two Majorana bound states at the edges of the wire. These are very special Bogoliubov-de excitations in the superconductor. These are 0 modes, which live at the ends of the wire, and together they form a delocalized fermion, a non-local fermion, which is the basis of all these Majorana-based topological qubits. So this was this proposal in 2010 by Ramon Lutzin et al. And Yuval Orech et al. And of course, you all know these experiments. I mean, Jelena already mentioned these zero bias peaks in tunneling conductance. These are the first experiments from Delft, DIDV against voltage and B field, and you see some zero bias anomalies. And since then, this was 2012, since then there have been many experiments showing pretty robust zero bias anomalies that are can be interpreted as coming from these Majorana bound states in the wire. But as Jelena mentioned, there is this ongoing discussion about whether these measurements can be interpreted in terms of Andreev bound states or Majorana states. And she also mentioned this review that we wrote together with other co-workers in Nature Review Physics, where we discuss the physics behind this Andreev versus Majorana interpretation in these semiconducting wires. All right, so this discussion is going on already for a few years. So my point is that let's try to explore different other options beyond the zero bias peaks. And here I want to focus on an idea of using Josephson junctions based on semiconducting wires. The idea is very simple. You just take a nanowire semiconducting wire, which will be the weak link in the Josephson junction, and you can gate this weak link. And in particular, I want to focus on systems where we include these nanowire-based Josephson junctions in superconducting qubits. So this idea was already realized experimentally in these two papers, 2015. These are the so-called GATEVOLTAGE. These are gate-tunable transmons. And the idea is that instead of controlling the Josephson coupling by means of a flux, like in a split junction standard SIS Josephson junction, you want to control with a voltage, with the gate, the Josephson coupling in the junction. And this, during the last few years, there have been many groups exploring this idea with nanowires and also with other materials, like here, for instance, with graphene Josephson junctions, van der Waals heterostructures, and so on. Apart from having the possibility of gate tunability, these systems are very interesting because we can try different hybrid materials combinations which have magnetic field compatibility. These material combinations are robust against large magnetic fields, and of course this opens the door to explore topological phases in this kind of hybrid qubits, and in principle to explore the combination of these transmon-like qubits with Majorana modes. All right, for those of you who are not familiar with transmons, let me just mention a couple of words. These are just superconducting islands with large charging energy, which is a standard charging energy term coming from this small island. And now we couple this small island to a superconducting reservoir by means of a Josephson standard SIS-Josephson junction, sin phi Josephson junction. This is the Josephson potential. And now we solve this problem, and depending on the regime of parameters that we are working, we can be in the so-called Cooper pair box regime, where the charging energy dominates over the Josephson coupling. In this case, what we have is just two Coulomb blockade parabolas for Cooper pairs. This will be the first parabola. This will be the second parabola for Cooper pairs. This is Coulomb blockade physics. But now these two parabolas get mixed here due to this Josephson coupling, and this avoided crossing here is used as a qubit. This was actually the first realization of a superconducting qubit. This is this Nakamura paper, experimental paper from '98, I believe. And now a very nice idea came from this group of people, Koch et al. In 2007, where they proposed to use a completely different regime, which is a regime where the Josephson coupling largely dominates over charging energy. In this case, we end up with a spectrum, which is essentially the spectrum of a harmonic oscillator, just slightly enharmonic. And the point is that we have now levels that are extremely flat against gate. So they are essentially immune against charge fluctuations. So these transmon qubits are very robust against decoherence, and they're actually the basis of all these nice quantum computers that we have these days. There's Google quantum computer, the IBM quantum computer, and so on. So as I said, this is essentially a harmonic oscillator. We have a slight anharmonicity, so we can still address independently this two-level system, and this would be my transmon qubit. All right. So the idea that I want to explore is to replace the SIS junction in a transmon qubit by an SNS junction formed by a nanowire. In this case, the Josephson current phase relation is no longer sinusoidal. This was already mentioned yesterday by Christian Sonnenberger. In general, we expect to have some arbitrary dependence on phase that depends on the Andreev levels that live inside this junction here. So by means of this gate voltage, I can tune the number of channels that I have in the junction, the transparency of the channels, and so on. So if I also apply a magnetic field, I can change the expression for this Andreev level. This is no longer valid if I apply magnetic fields, and so on. So I can actually tune the critical current of the junction by means of a gate voltage, and hence change the frequency of the transmon qubit, and hence the name gate tunable transmon, gatemon. And as I said, these are these two experiments that showed this behavior. And here you see how the frequency of the qubit changes against the gate voltage, or here. And also interesting is that in a circuit QED geometry, you can include these nanowires and actually show that the qubit is strongly coupled to the resonator, and this is a blow up around this region. This green line would be the resonator. This is a blow up where you see these avoided crossings showing a strong coupling between this gatemon qubit and the resonator. All right, so So the idea is now to increase magnetic fields and see what happens to this gate mon in the presence of Majoranas. So apart from the Josephson coupling that I get from this SNS junction physics, if I am in a topological regime, I also expect to have Majoranas living nearby the junction. So there is a new term apart from the standard Josephson coupling that comes from these Majoranas, which transfers electrons one by one. And this comes from the fact that, as I mentioned at the beginning, that two Majoranas together form a fermion. So I can share a fermion, a single electron between two Majoranas, all right? So I go from this situation to this situation, and I have a one electron transfer. This is this cos phi over 2. This is this famous 4 pi Josephson effect in Majorana-Josephson junctions. And the amplitude of this Josephson term would be EM. Sorry. All right, because I have this transfer of single electrons, I have to consider two possible parities in the junction. When I transfer one electron here, the left and the right segment now contain one extra electron each. So I need to consider both this even parity in the left and right sectors and odd parity in the left and right. So the problem becomes parity degenerate. Each of the levels of the original levels of the qubit are now degenerate due to this parity coming from the Majorana coupling. So the picture that we have in mind is that each of these transmon levels has now this fermion parity degeneracy, and because of the Majorana coupling, each of the transmon lines will split. So this splitting of the transmon lines will be a very strong signature of Majoranas in the junction. This idea was first put forward by Ginoser and Grossfeld in this paper here, where they studied a standard transmon model with this standard Josephson coupling, and they just studied this problem in parity space. This is now a matrix in this parity space, and they just consider two copies of a transmon that are coupled through this Majorana that they included by hand. So this is like a toy model for studying this kind of physics. And indeed, they studied how all these transmon lines split due to the presence of this off-diagonal of this Majorana term. And also similar paper appear later on where they studied similar models. All right, this idea is very attractive. So take a gate mon, put magnetic fields, and see whether you see a splitting of the qubit lines coming from Majoranas. So there are already a few experiments trying to see these so-called transmon Majorana qubits. This is an experiment from Charlie Marcus's group in Copenhagen, where they study these nanowire-based transmons with full shell nanowires, full shell meaning a nanowire that is fully covered by superconductor. In this case, these full shell wires show little Parks oscillations. This was shown in this science paper by the same group, where you see these little Parks oscillations of superconductivity, and even at one flux quanta, when one flux goes through the wire, they saw these zero bias anomalies that they interpreted as zero bias peaks. So what they do is to study these full shell wires in a transmon configuration. They indeed see this magnetic field dependence of the gate mon frequency, and this comes from the fact that you are modulating the gap of the superconductor. But now they fix magnetic field and they study the spectrum of the drive against gate voltage, and they indeed see both parity branches. This is even an odd parity branch. At zero magnetic field, we expect that these two branches should be degenerate, of course, because there is nothing inside the gap. But the surprise comes when they study these experiments in the middle of the first lobe, when they see both branches, but they are not they don't anti-cross. There is no finite coupling between the even and odd branches. So it seems that this Majorana coupling coming from this zero bias peak here in this experiment is not active somehow. And they actually put some bounds for this coupling. They say that the coupling, the Josephson coupling, is around 5 gigahertz, while the Majorana coupling, the lower bound, is below 10 megahertz, which is kind of strange actually, because they have very strong zero bias peaks in their experiments. There is a second experiment, in this case also from the same group, in this case studying a double island experiment, essentially a kind of double dot experiment with superconducting nanowires. And the point that I want to stress is that they are also able to extract the Majorana coupling for these islands, but in this case the surprise comes from is kind of the opposite behavior. Now the single electron coupling is very large, is of the order of 10 gigahertz, while the Josephson coupling is of the order of half a gigahertz. And actually they are in a very special regime where the charging energy is by far the largest energy scale. This is 40 gigahertz. So this is no longer a transmon. But the important point is that they can reach regimes where the Majorana, well, the single electron coupling that they extract from microwave is much larger than the Josephson coupling, like the opposite that we had with the full shell wires. So these two experiments, I included them in the talk just to illustrate that we actually need a microscopic calculation that is able to explore different parameter regimes for these nanowires from kind of microscopic models. So what we do, in all the details are here in this paper that we recently published. What we do is to start from the Luchin-Oreх model for each of the segments. The left and right segments would be Luchin-Orech wires with the chemical potential, the spin orbit coupling, and the external Zeeman field. We now construct a Josephson junction out of these wires. We have some coupling between these two wires, and we construct a BDG Hamiltonian, a Bogoliub of the Jens Hamiltonian, and we study the quasi-particle excitations, the BDG excitations of this Luchin-Orech Josephson junction. All right, so let me remind you about what we should expect for the spectrum of each of the segments before doing the Josephson junction. Each of the segments as a function of magnetic field, what we expect is the closing of the gap. As we increase magnetic field, the superconducting gap closes at the critical field and then reopens again. This is the topological transition. And together with this gap closing and reopening, we have this orange line here that goes down in energy and then stays there close to zero energy. This is our Majorana zero mode. In this case, this Majorana zero mode is oscillating. You have some finite delta here, and you have some points where this oscillation goes to zero. And these oscillations come from the fact that we are considering finite length nanowires. So they overlap, and hence we have some oscillatory behavior of the zero mode. All right, so if we take this spectra and now we study the full Josephson junction inside a transmon cavity, or inside, in general, a superconducting qubit model, this is what we expect. At zero magnetic field, each of these orange lines, which are the odd excitations, live at the gap at delta. So my odd excitation is 2 delta. And the blue lines are the even parabolas, the standard Cooper pair box parabolas. Here I'm considering that the coupling is zero, just in order to illustrate how the parabolas behave. Now I start to increase magnetic field, so I start to move down in energy with the orange line. This orange line goes down in energy until I reach the critical field, in which the orange line, the odd parabola, is degenerated with the even parabolas. Now I put some finite coupling across the junction, and we, at zero magnetic field, of course, we see this avoided crossing between even parabolas. This is a standard Josephson coupling. As I increase magnetic field, I see both Josephson coupling and this Majorana coupling that mixes the odd and the even parabola. And as I said, now these parameters, EM, EJ, delta, and so on, depend on microscopic parameters as compared to the previous theory papers, depend on microscopic parameters of the wires. Like, for instance, EM depends on the topological gap, and this topological gap depends on the spin-orbit coupling, the magnetic field, chemical potential, and so on. Delta, which is the energy splitting, will depend on the length, the coupling of the junction, and so on. Importantly, the ratio between the EM, the Majorana coupling, and the Josephson coupling is this ratio between a square root of transmission times the topological gap over transmission times the standard gap. So this quantity is not necessarily small. Depending on transmission across the junction, I can go from regimes in which this ratio is smaller than 1 to regimes, as I reduce the transmission, to regimes with this ratio is larger than 1. And also it would depend on the topological gap, which again is the distance between this excitation leaving at 0 energy and the next VDG excitation in my wire. And this topological gap, again, depends on microscopic parameters. All right, so now we have all the ingredients to study this kind of superconducting qubit spectra from microscopics. Now we can extract EM, delta, and EJ out of our Luchin-Oreх model. And in what we do is to solve this Strasmon model plus this generic Josephson potential that I obtain out of my VDG description of the wire. And in particular, these three quantities can be written in terms of matrix elements of the Josephson potential. I don't have time to give you details. Let me skip this kind of technical slide, but let me just mention that what we do is to trace out all the levels above the gap. So this would be the bulk contribution. This quasi-continuum of levels living above the gap would give me my bulk contribution that replaces the cos phi term in a standard junction. And then I keep track of the subgap Hilbert space, which is the Hilbert space of the 4 Majorana modes that interact in the junction at low energies. So by doing this partition, this projection technique, we are able to write the Josephson potential in terms of bulk and subgap contributions, and we can write this kind of matrix that replaces this kind of toy model-like description that we had in this previous paper. And all these matrix elements contain microscopic information about the wires. Let me now show you how the microwave spectra, this is the matrix element of the number operator between eigenstate of this superconducting qubit model, behave as a function of magnetic field. And let me focus in particular on what happens around one of these parity crossings. Red is a bit before the parity crossing, yellow is right at the 0 energy crossing, and blue is after the 0 energy crossing. Here I'm changing magnetic field. All right, when the Majorana coupling is much smaller than the charging energy in this regime, what we have is something very similar to what was discussed before in the previous papers. We have the transmon, the qubit line, and as I increase magnetic field, I see the splitting of the transmon line, and this splitting is essentially depends very little on magnetic field. So just a standard splitting of a transmon line coming from this Majorana coupling, and this is in agreement with these previous papers. And this is in the regime where the Majorana coupling is much smaller than the charging energy. And remember that there are experiments with very small Majorana couplings. Let me now discuss the opposite regime where the Majorana coupling is larger than the charging energy, and this can happen with realistic parameters. And again, let me show you the spectrum of the wire against of the island against magnetic field. Near one of these parity crossings, this orange line would be my odd excitation. This blue line would be my even ground state. Before, my ground state is even, but after the crossing, my ground state now is odd, and vice versa when I cross again. So I have changes in parity of the ground state, and when the Majorana coupling is larger than the charging energy, these changes in the ground state change completely the spectrum, the microwave spectrum. So you have to compare this spectrum here that we had before with this spectrum now. What we have now is a transmon line at low magnetic field that now splits into multiple lines. And very interestingly, before and after the crossing, there is a switch, a very abrupt switch in the transmission line, in the microwave lines. And this switch can be understood as a complete switching of spectral weight. These are the transitions weighted by their matrix element. The width of the line is the matrix element. There is a complete switch between matrix element between this line, or this line and the other line. And these switches can be actually understood, this spectral transfer weight can be actually understood as exact 1 electron transfers across the junction. So this is for fixed magnetic field, how the spectrum looks like against a gate voltage. And you see how before and after the crossing, there is 1 electron shift, exact 1 electron shift between this plot and this other plot. If you compare this minimum here, is this minimum there, or this minimum here, is this minimum there, and so on and so forth. So there is a complete switch of 1 electron in the spectrum. And very interestingly, right in the middle of the parity crossing, when the system, the oscillation goes to 0, I recover a standard transmon. So this is very, very, very interesting feature that can be, I mean, if this is seen experimentally, this is a very strong signature of Majorana oscillations. I see 1 electron shift from one to the other. In the middle, I have a pure transmon line in my spectrum. So we believe this is a very clean and very nice signature of Majoranas in the junction that does not need the use of tunnel junctions, tunneling spectroscopy, and so on, zero bias anomalies that lead to all these ambiguities in the interpretation of the data. All right, so as I said, all these switches and so on can be understood from the changes of parity of the ground state. We go from even parity to odd parity in the ground state. And all these transitions, if you are interested, please go to the paper. All these transitions can be understood. This is a very long paper where we study in detail all the matrix elements, all the possible transitions of the island and so on. And this can be really nicely understood. And we also study other regimes, which include regimes where the charging energy is very large, like the one in the experiment that I showed before, also split junctions and so on. So please go to these 2 references. So the take-home message would be that we believe that these nanowire-based superconducting islands are a powerful or promising experimental tool to explore Majorana physics. And in particular, in the talk, I've been discussing this new regime where the Majorana coupling over the charging energy is not negligible or can be even larger than 1, and how this regime is very interesting actually to extract precise information about Majorana oscillations and parity crossings in the junction that are unique to Majoranas. And with this, let me thank my co-workers, Jesus, Pablo, and Elsa, and in particular, Jesus, who is my PhD student. He has been behind all these calculations that I showed today, and also all the calculations in these 2 papers. And with this, I thank you for your attention, and I finish. Thank you very much.